Okay, so question for you. Is the hydrogen molecule really the simplest molecule? No, there's actually one molecule simpler. It is the H2 plus ion. So while the hydrogen molecule is the simplest neutral molecule, we can do a little bit better in terms of solving our Schrodinger equation by going to an ion of a molecule. Okay, so in this case, we can eliminate the electron-electron repulsion term and solve our Schrodinger equation exactly, because again, for the hydrogen molecule ion, we're still working within a one-electron system, which is the only system that we can solve the Schrodinger equation for exactly. Once we have solutions to the H2 plus molecular ion, we can use that as a starting point for approximating wave functions for other multi-electron systems. So that's kind of like how we used hydrogen as a starting point for our previous multi-electron atoms. All right, so where should we start in solving our hydrogen molecular ion? Unfortunately, the exact treatment of H2 plus yields pretty complicated wave functions, and they don't lend themselves terribly easily to the study of multi-electron molecules. So what we'll do is to fall back on our trick of linear combinations to obtain accurate approximations to the hydrogen ion molecule wave functions that can be used to construct wave functions for many electron diatomic molecules that we might be interested in. This is called linear combination of atomic orbitals, or abbreviated lcao. So this is a very common approach to coming up with sample wave functions for more complex systems. We've seen this idea before in the class where we have linear combinations that we use to put together wave functions for different systems. Okay, it's the same idea here, except the functions that we're going to be combining are functions that represent atomic orbitals. You'll also hear the linear combination of atomic orbitals referred to as basis sets in computational approaches. Okay, so if you were to use variational theory to determine an approximate value of the energy of the hydrogen molecular ion, what would you propose as a trial function? Well, probably some combination of one electron, one s wave functions that you specify for the two nuclei involved, and then you can even include a variational parameter to kick your calculation up a notch. Okay, as a first approximation, we can represent the electronic wave function of H2 plus by the following expression. So here, our wave function is just a combination of normalized 1s wave functions associated with atoms A and atom B. Okay, and then psi, again, would represent our trial function, which we are familiar with from our variational calculations. Okay, so this is what we would consider to be a minimal basis set calculation. So it's just a very simple combination of functions. Okay, we can get much more complex, add many more terms to this trial function, extra variational parameters to get better calculations. Okay, but this very simple combination here that we're using would be termed a minimal basis set. Okay, so the other thing that we would be interested in obtaining here would be the constants, the linear combination constants out front, which tell us essentially if you take the square of these, remember, it gives you the relative contribution of each one of those terms to the total function. Okay, so those constants have to be evaluated using the variational method. So this is something that has been described previously in your Macquarie textbook and other textbooks. It's a very standard approach, and you can go back and take a look at that if you want to see the details of this process. But I'll just walk through the highlights of the solution using the secular determinant method. Okay, and we can use that secular determinant, or we can obtain a secular determinant, I should say, because our trial function depends linearly on these variational parameters C1 and C2. Okay, so this is just a kind of a handy trick that is possible when you have that linear dependence on your variational parameters. So not always the case, but here it will work for us. Okay, so an outline of the process is you're going to set up your variational calculation. So hopefully this looks familiar to you as the calculation of the energy using the variational method. Okay, you would then, after you set up this expression, you would take the derivative of the energy expression with respect to each variational parameter, so dE dC1 and dE dC2, and set both of those derivatives equal to 0. Okay, so what we're doing here in this step is essentially working to minimize our energy. Okay, so this is the key that's happening there. So minimizing with respect to the variational parameters. Remember, we always want the minimum energy level for these types of calculations. And then after doing that, you will be able to assemble your resulting expression into what we call the secular determinant, which would be set up as such. Again, the details of all the in-betweens where these green arrows are, those are detailed in pretty much any quantum chemistry textbook that you can pick up. So feel free to refer to that for the details of those steps. So we'll keep it short for the sake of this video. So once you set up your secular determinant, okay, then we can start to extract some information out of it. So just a couple of things regarding this secular determinant, the matrix elements that are contained in here. So just some notes here, the HAA terms are described by these integrals, okay, and make note that HAA is equal to HBB in this case, okay, and then we have the definition of our those are called, given a special name called the Coulomb integral, okay, when you're working with the wave functions on the same atom, okay. It's kind of like you're just calculating the energy right on each individual atom, okay. And then you have the combo of atoms A and atoms B that represent your HAB term or your HBA term in the matrix elements. Okay, so those values there are called resonance integrals. You may also see them referred to as exchange integrals. Okay, so that's where you have the mixing of your two nuclei. All right, and then there's the S's. So we have SAA and SBB. Okay, so these are just essentially your normalization conditions. Okay, so when you are looking at the same nuclei in those integrals, obviously you're going to get your normalization result of 1. Okay, if they are different nuclei, okay, then you'll have this value of S that comes out. Okay, so not necessarily 1, not necessarily 0, okay, but it's going to be somewhere in between your 0 and 1, somewhere in between essentially your orthogonality and your normalization situations there. So this S that you calculate has a special name called the overlap integral. Now this overlap integral is essentially a measure of the overlap of the individual atomic orbitals. Okay, so that S value will be larger when your atoms are closer together. And it turns out that bond formation requires that that term has to be greater than 0. Okay, so this caveat here tells you which one of these is kind of what we're going to be zeroing in on when we start thinking about whether or not two atoms are going to come together and form a bond or not. Okay, so it's that overlap integral that is the important part of that puzzle. Okay, so next step in this process is going to be to evaluate the secular determinant that we came up with on the previous slide. So again, remember evaluating a 2 by 2 determinant, you multiply your cross terms and subtract that second cross term, set it equal to 0. Okay, that allows you to end up with this relationship, and then we want to, again, our item of interest is always going to be that energy. So we're going to rearrange and solve for E. So maybe this would be a good time to pause the video and just satisfy yourself that you can get from here to this expression, and then from here to these two options for your energy roots. Okay, so hopefully you're satisfied with how we got to this point where we have these two expressions for our possible energy roots. It turns out when you evaluate the resonance integral, it's found that it is negative. Okay, so remember that resonance integral is that that one that corresponds to the mixing of both of the nuclei A and B. Okay, so that that fact makes E1 the lower energy root. So this is going to end up representing our ground state energy. All right, and then just to finish things up with the calculations, if you want to obtain the coefficients C1 and C2, okay, that we mentioned before, then you just want to go back and use the algebraic equations that lead you to the secular determinant. Okay, so that would be, again, we're doing that minimization. Okay, so you have two equations, two unknowns, and you can figure out the values for C1 and C2 with that root. Okay, so now let's take a look at the interesting stuff here. So one question you might have is, what does our wave function look like when all of this is said and done? Okay, so what do the wave functions look like as our two atoms, A and B, start to get close to one another? Okay, this is where we ask ourselves, are they going to form a bond, or are they not going to share that electron density to form a covalent bond? Okay, so what we have here are images of our two options for our energy. So remember here, this is our lower energy root, okay, and then we have our higher energy root. So the only thing that's changing there are the signs, okay. So here it's the positive signs, and here are the negative signs. So for the positive situation, what we end up experiencing here are two wave functions. So if you can see the purple outlines here, those are the individual, essentially 1s like wave functions on each individual atom, okay? And then what's happening in the middle here is those wave functions are constructively interfering with one another because you have two, we can sort of say that these are both the same sign, right? Okay, so as those two functions start to kind of move towards each other, they're going to, based on the signs of those functions, they're going to constructively interfere with one another. And what happens then is that results in overlap in that region that we discussed earlier. So that would be kind of representative of the S overlap if you're thinking about the equations. Okay, so this S is going to be a positive value. If, however, we have opposite signs of the wave functions that are coming together for these atoms, then again, let's say here we have plus, and we'll call this one minus. Okay, so again, remember opposite signs here. Okay, so when you have opposite sign functions coming together, they're going to essentially destructively interfere with one another. So when we look in that region of overlap, right here between the two atoms, which is where our bonding happens, right? That's This is the region or internuclear region where we're concerned with in terms of figuring out whether a bond is going to happen or not. There's destructive interference going on in that region. Okay, so if we look at these two wave functions overlapping with one another, we see that there's very little overlap, very little kind of constructive interference. In fact, there's no constructive interference in this case between these two functions. Okay, so in this case, we get good overlap with the same signs. Okay, that tells us that we're going to have this resulting blue curve here where we get a nice amount of probability of finding our electrons there. Okay, so this is essentially telling you that you're going to be sharing electrons between those two atoms in that region between your nuclei. Okay, looking over here, when these two oppositely signed wave functions come together, they destructively interfere. We get the resulting blue curve. Hopefully you can see that distinction there. And then if we look at the point that matches up with our internuclear area there, our overlap area, we see that there's 0. So if you were to calculate the probability, right, your probability of finding your electron in there in that region, you would see that it would be 0, right? So if you square that, still going to have a nice big fat 0 there, which tells you that you're not getting any overlap, which tells you that you're not forming a bond, as opposed to over here where we get a nice non-zero number there. Okay, so hopefully you can start to get a sense of the fact that a stable covalent bond is formed due to the overlap of atomic orbitals on your relative nuclei, so nucleus A and nucleus B, okay, or overlap of your atomic orbitals 1s-A and 1s-B. Okay, that overlap integral, fun fact, the overlap integral here that is so important for us in looking at whether or not we're going to have a good bonding situation is often neglected in some computational chemistry methods. So if you're using things like semi-empirical methods in a Spartan or Gaussian kind of program, then you're probably doing a calculation that neglects that important term. So just keep that in mind. Okay, so that's an intro to the method of linear combination of atomic orbitals, or LCAO theory. So by combining individual atomic orbitals on each atom, we observe either constructive or destructive interference between the wave functions in the region of overlap that's going to either favor or disfavor bonding. Okay, so next we're going to look more closely at how the linear combinations of atomic orbitals will lead to our familiar molecular orbitals that you know and love from organic chemistry and some of your other chemistry classes. All right, thanks.